Hey YouTube, and welcome to Tech Talks. Today we're going to be talking about Big O notation and algorithm runtime analysis. If you're anything like me, I was super confused when I first started learning this stuff, but I promise you that by learning the patterns I'm going to share in this video, and with a little bit of practice, you too can master this concept. Being able to analyze your algorithm runtime is super important, not only for software engineering job interviews, as it comes up quite a lot, but also to be able to determine if the code that you're writing is efficient. Trust me, if you take the time to learn this topic as soon as you can, you will give yourself a great head start in your ability to write efficient code. If you're new to this channel, welcome. If you want to hear about various computer science and software engineering topics, from programming tutorials to deeper topics like continuous integration, continuous delivery techniques, to even more advanced topics like architectural design and much more, please hit that subscribe button and click the bell icon to be notified about when I upload new videos. Now, let's start learning about Big O notation and algorithm runtime analysis. So let's start off with a little story. Meet Timmy. Timmy has an idea for a new startup that will give its users the ability to watch videos. For now, let's call the company FlixNet. Now, Timmy starts out by telling his customers that if they purchase a monthly subscription to FlixNet, he will send them up to 4 DVDs per month. They can order the DVDs to arrive all together, or they can order them separately to arrive on different days. For argument's sake, let's assume that the customer orders all 4 DVDs at once. Timmy then sends the DVDs and it takes 2 days for them all to arrive together. If the customer orders 3 DVDs, Timmy sends them all and they still take 2 days for them all to arrive together. And the same is true if the customer orders 2 DVDs and 1 DVD. It will always take 2 days for the DVDs to be shipped and arrive at the customer's home. Since it always takes 2 days for any amount of DVDs to arrive, we refer to this process as taking constant time, or Big O of 1. No matter how many DVDs are sent, it always takes the same amount of time. Timmy could decide to send thousands of DVDs and it would still be true. It still takes 2 days. Or, as we've learned, constant time for the customer to receive them. But wait, Timmy has another idea for a new business model where instead of shipping the DVDs through the mail, he will upload them to his server and send the customer a download link on his website. Now, instead of sending a movie out via the mail, it will take just 1 hour for the movie to download. The only caveat to this model is that it takes each movie 1 hour, for argument's sake, to download to the customer's computer. The number of movies directly ties into how much time it takes. But that's still great. If the customer wants to download 2 movies, it will take just 2 hours to download. If the customer wants to download 3 movies, it will take 3 hours to download, and so on. We refer to this as linear time, or Big O of n, with n being the number of movies that the customer wants to download. Instead of having to wait 2 days to receive up to 4 DVDs, the customer can now download 4 movies in just 4 hours. A much better and faster process, right? Well, as it turns out, not exactly. In the very near future, Timmy is going to make a business decision at FlixNet and allow the customer to download 100 movies per month. Let's look at how that changes our algorithm runtime. If the customer was to go with option 1 and have the 100 DVDs shipped to them, it would take 2 days for them all to arrive. However, if the customer was to go with option 2, then it would take 100 hours for all of the movies to download. That equates to just over 4 days. At first, constant time seems to be the slowest and the linear time to be much faster, but because the number of movies we were dealing with has changed dramatically, the constant time process actually turned out to be much faster. And that is why it's important to know how the speed and efficiency of your algorithm can change. So let's talk about best case, worst case, and expected case as it relates to algorithm analysis. The best case is the function which performs the minimum number of steps, the worst case is the function which performs the maximum number of steps, and the average case is the function which performs an average number of steps on input data of n elements. The term best case performance is used in computer science to describe an algorithm's behavior under optimal conditions. For example, the best case for a simple linear search on a list occurs when the desired element is the first element of that list. When talking about algorithm runtime analysis, software engineers rarely ever use the best case to describe an algorithm because it would be very impractical. Instead, we usually always use worst case. So, it should always be assumed that a simple linear search on a list will take big O of n time, because in a worst case scenario, the value we're trying to find might be at the very end of the list. So while it's not as heavily discussed, if we're going to talk about time complexity, it's worth quickly mentioning space complexity. Space complexity is analysing the amount of memory, or space, that an algorithm will need to compute. The theory behind space complexity is almost identical to time complexity. If the algorithm requires a single array of size n, then it is said that the algorithm will require big O of n space. If a two-dimensional array is used, it is said to require big O of n squared space. Now back to runtimes. In this graph you can see the most common algorithmic runtimes. Although there are many more, these are the most frequently talked about. So let's take some time to go through them, and I'll teach you some super helpful tips about how to identify them based on the steps in your algorithm. Big O of 1, or constant time, as we've already discussed, will occur when the algorithm will take the same time to complete no matter what data is being passed into our algorithm. From our very basic FlixNet scenario, we know that it will take the same amount of time to physically ship the movies to the customer no matter how many movies are ordered. A real-world example would be the following algorithm. As you can see by the code, we are accessing the second index in a given array. It doesn't matter if the algorithm receives an array with 5 elements or 55 elements or 500 elements, it will only return the value at index of 2, so the runtime is constant. Some other examples of algorithms that would take a constant time are inserting a node in a linked list, pushing and popping on a stack, insertion and removal from a queue, finding out the parent of the left or right child of a node in a sorted tree, or jumping to the next or previous element in a doubly linked list. Remembering our FlixNet example again, we can think of the business model of letting the customer download each movie in their package, with each movie taking exactly 1 hour to download, as linear time, or big O of n. This happens when the amount of time it takes to complete the algorithm is directly tied into how large the data set is that the algorithm is receiving. A real-world example would be a simple linear search algorithm. As you can see in the code, we are trying to find the value of integer n in an integer array. In the worst case scenario, we will have to search through the entire list before we find our number. That is, we will have to visit every element in the array of size n. Therefore, this algorithm is described as big O of n. Some other examples of algorithms that would take a linear time are traversing a linked list, linear search, deletion of a specific element in a linked list that is not sorted, comparing two strings, or checking for a palindrome. Big O of log n is a fairly straightforward algorithm to spot. Let's think about how binary search works. Given an array of sorted elements, for example an array of integers, we want to find n. Binary search starts by looking at the middle number of the array and checking if it is less than, equal to, or greater than n. If n is equal to the middle number, then we have found our number. If n is less than the middle number, then we search again using the first half of the array. If n is greater than the middle number, then we search again using the second half of the array. Then we continue on, splitting the array in half with each step until we have found our number, or we are left with just one number to check. If you ever find that your algorithm splits in half with every step, it is a clear indicator that your algorithm most likely has a runtime complexity of big O of log n. Some other examples of algorithms that take big O of log n time are finding the largest or smallest number in a binary search tree, or certain divide and conquer algorithms based on linear functionality. Big O of n log n is a runtime that looks kind of daunting the first time you read it, but in reality it's quite simple once broken down. With this runtime, all we're doing is piecing together big O of n and multiplying it with big O of log n. That is to say, for every time we run big O of log n, we have to also run big O of n. To give a real example of this, let's think about how merge sort works. We start by recursively splitting the list in half until we are left with single elements, which is our big O of log n portion. And then we iterate through the list each time we return up the call stack, which gives us our big O of n example. In the end, this gives us a very stable algorithm to sort an unsorted array of elements. Some other examples of algorithms that take big O of n log n time are merge sort, heap sort, and quicksort. Big O of 2 to the power of n denotes an algorithm whose growth doubles with each addition to the input dataset. The growth curve of this runtime complexity function is exponential, starting off very shallow but then rising meteorically. An example of a big O of 2 to the power of n algorithm is the recursive calculation of Fibonacci numbers. Let's consider the following algorithm. As we can see by looking at the implementation, for every call to Fibonacci, we are making 2 extra calls to Fibonacci. If we take a look at how this might translate to a tree structure describing our calls, we can see that every call splits off into 2 branches until we are at the leaf nodes. In general, but not necessarily always, if you spot an algorithm that is making multiple recursive calls, you can assume that the runtime will be big O of branches to the power of the depth. The final runtime that I'm going to talk about today is big O of n squared. It is easy to identify this runtime because you will usually see one loop that iterates through some input data, which in turn has another nested loop that iterates through the data for every element in the array. If we were to add another nested for loop that parses the same dataset, the runtime would become big O of n cubed, and so on for every additional nested for loop that parses the same dataset. A great example of a big O of n squared algorithm is bubble sort. Bubble sort is a simple sorting algorithm that works by comparing each pair of adjacent elements and swapping them if they are not in order. By looking at how our dataset changes as we step through this algorithm, we can see that the highest values bubble up to the end of the dataset, hence giving the name bubble sort. In the worst case scenario, that is, if all the elements in the dataset are completely out of order, the dataset will have to be parsed once for every n elements in the array, which equates to n squared. As an enhancement to bubble sort, we can track to see if a full pass of the dataset has been made where there were no swaps, and we can break out of the algorithm knowing that our dataset is fully sorted. But remember, we always want to use the worst case scenario when describing the runtime of our algorithms, which for bubble sort is big O of n squared. If we look at the implementation of bubble sort, we can see that there is one nested loop that iterates through the input data inside another nested loop that iterates through the input dataset. This is a clear indication that bubble sort has the runtime complexity of big O of n squared. Some other examples of algorithms that take big O of n squared time are insertion sort, selection sort, and traversing a simple 2D array. So that wraps up this tech talk on big O notation and algorithm runtime analysis. But before you go, I have a challenge for you. Let's take a look at a simple algorithm, and I want to hear what you think the runtime complexity is. This one is a little bit tricky and might not be the runtime that you initially think of, so be sure to pay close attention before giving your answer. How would you use big O notation to describe this algorithm? Leave a comment down below, and don't forget to like this video and hit that subscribe button. If you want to see how you can apply some of your new runtime complexity knowledge when solving programming questions, check out the featured video on the left. Or if you want to dive into something a little bit different, check out the featured video on the right. Thanks for watching, and I will see you next time on Tech Talks.